What if that chair you're sitting on, or the phone in your hand, even the air you're breathing, only truly becomes solid when you look at it? Seriously. Imagine a world that kind of waits for you to glance its way before it decides what to be. Now, this isn't some plot from a wild sci-fi movie. It's a real question stemming from quantum mechanics, which, by the way, is one of the most tested and mind-blowingly accurate theories we humans have ever devised. Get ready, because what you think is solid and real, it's about to get a major shakedown. For ages, we've all pretty much agreed that reality is, well, real, objective. A tree falls in the forest, it makes a sound, right? Whether anyone's there or not. Things possess definite properties, like their location, their speed, their color, irrespective of our observation. That's the world of classical physics, the physics of our everyday lives. But shrink things down to the teeny tiny world of atoms and particles, and the rules don't just bend, they absolutely shatter. Quantum physics unveils a universe that's far stranger, far more mysterious, and much more tied to us observing it than we ever dreamed. So today, we're taking a trip into this quantum realm to explore one of its most mind-boggling ideas, that the world around you might not truly exist, at least not in the way you think it does, until you actually look at it. We're going to investigate this quantum truth about how merely looking at something can change the outcome, and it might just shake the very foundation of how you perceive, well, everything. Our everyday world largely plays by predictable rules. Kick a ball, and you can pretty accurately guess its trajectory. It always has a definite position and a definite speed. We just assume that's how everything works, everywhere. But back in the early 20th century, when physicists began probing the world of atoms and their constituents, like electrons and photons, they encountered phenomena that defied classical sense. They discovered a world governed by probabilities, not certainties. A world where tiny particles could genuinely exist in multiple places at once. This is known as superposition. Think of it like a coin spinning in the air. It's neither heads nor tails until it lands and you observe it. Quantum particles, before measurement, exist in a similar fuzzy cloud of possibilities, described by what's called a wave function. This wave function doesn't tell you where a particle is. It tells you the probability of finding it in a particular state or place if you decide to look. Then there's another incredibly weird phenomenon: wave-particle duality. Light, for instance, sometimes behaves like a wave, spreading out, creating interference patterns, much like ripples in a pond. Yet, at other times, it acts like a stream of tiny projectiles or particles called photons. The same electron can embody both of these seemingly contradictory natures. This inherent fuzziness, this world of maybes, isn't due to flawed tools or missing information. It appears to be the fundamental nature of reality at the quantum level. It's a kind of strangeness that renders our normal intuitions almost useless. Perhaps the most renowned example of quantum weirdness, the one that truly throws a wrench into our classical view of reality, is the double-slit experiment. Picture this: you're firing tiny particles, like electrons, one by one, at a barrier with two narrow slits. Behind this barrier, a screen detects where each electron lands. Now, if electrons were simply tiny marbles, you'd expect to see two distinct stripes on the screen, right? One for electrons passing through one slit, and one for those going through the other. And sometimes that's precisely what happens. But here's where it gets truly wild. If you don't attempt to determine which slit each electron passes through, something astounding occurs. The electrons, despite being fired individually, create an interference pattern on the screen, a series of alternating bright and dark bands. This is pure wave behavior. It suggests each electron somehow passes through both slits simultaneously, like a wave, and then interferes with itself. How crazy is that? Okay, now for the kicker: the observer effect. If you place a detector at the slits to ascertain which path each electron takes, that interference pattern, poof, it vanishes. Suddenly the electrons behave like well-mannered little particles, passing neatly through one slit or the other, and you merely get those two simple stripes on the screen. The very act of observing, of measuring which slit the electron traversed, completely alters the outcome. It's as if the electron knows it's being watched and decides, all right, particle time. This isn't just a minor nudge. It's a fundamental shift in what's actually occurring, all because we chose to look. So this naturally leads one to wonder, what exactly is an observation or measurement in quantum mechanics? Does it necessitate a conscious observer, like you or me, to be looking? Well, the concise answer, according to most physicists, is not necessarily. In quantum mechanics, observation or measurement typically refers to any interaction between the quantum entity, like our electron, and a larger measuring apparatus, or even just another particle. This interaction essentially forces the system to choose a side from its array of possibilities. This causes the wave function, the cloud of all possibilities, to collapse into a single definite outcome. Thus, a Geiger counter clicking for a radioactive particle, a photon striking a detector screen, or even an air molecule colliding with a tiny speck. All of these can qualify as a measurement. They effectively record some information about the particle's state, and that recording is the crucial aspect. But, and it's a significant but, the whole consciousness question has been a fervent topic in philosophy since these discoveries. Some early quantum pioneers, and some contemporary thinkers, have pondered whether consciousness itself plays a more direct role in making reality, well, real. Concepts like the von Neumann-Wagner interpretation actually propose that consciousness is required to complete the measurement process. The eminent physicist John Wheeler even spoke of a participatory universe, implying we're not just spectators. We're involved in creating the reality we observe. Now, these are incredibly fascinating ideas, genuinely pushing the boundaries of our understanding. However, to be clear, there's no scientific consensus that human consciousness, specifically, must be present for the observer effect seen in experiments like the double slit. An interaction with a measuring device is sufficient. Still, that philosophical door is undeniably ajar, compelling us to ask some truly profound questions about reality and our role within it. So if simply measuring something is key to the properties it exhibits, what does this quantum truth genuinely tell us about reality itself? One of the oldest and most established interpretations is the Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg. It essentially posits that entities in the quantum world, like an electron's position or momentum, don't actually possess definite values until they are measured. Before observation, the system exists in that fuzzy superposition of all possible states. Therefore, reality at this profoundly fundamental level is about probabilities and only crystallizes when something interacts with it. Bohr even contended that we cannot truly know or even discuss what an electron is doing when we're not observing it. Quantum mechanics is a toolkit for predicting what we'll observe when we do look, not necessarily for describing some independent reality that's perpetually there in the conventional sense. This entire notion that reality is somewhat up in the air until measured is, understandably, quite unsettling for our everyday cognition. Albert Einstein famously detested this aspect of quantum mechanics. He once sarcastically questioned if the moon only exists when we look at it. He was convinced there had to be a deeper, more complete narrative to reality that we simply hadn't uncovered yet. Then there's another mind-bender, the many worlds interpretation, MWI, conceived by Hugh Everett. MWI essentially examines the mathematics of quantum mechanics and asserts, let's just assume it's always correct, no exceptions. Consequently, there's no collapse of the wave function. Instead, every time a quantum measurement occurs with multiple possible outcomes, the entire universe bifurcates into multiple parallel universes, one for each outcome. So if a quantum coin flip could result in heads or tails, then in one universe it lands heads, and in another, it lands tails. You, the observer, also split. All these worlds are equally real, but they generally don't interact. It sounds utterly wild, right? But this idea elegantly dispenses with that problematic wave function collapse, and many physicists take it seriously because it treats the quantum rules as universally applicable, even to us in the entire cosmos. So whether it's Copenhagen's reality on demand or many worlds' ceaseless branching realities, the message is quite clear. The solid singular, out there reality we typically believe in, it might be a grand illusion, or at the very least, vastly more complex and participatory than we ever conceived. And consider this, recent experiments are still pushing these concepts, with some research even suggesting that facts, or measurement outcomes, might depend on the observer, further blurring those lines of objective reality. And this quantum strangeness isn't confined to quirky thought experiments. It has tangible effects and applications in our world. Take quantum entanglement, for example. Einstein famously dubbed it spooky action at a distance. When two particles become entangled, their fates are linked, regardless of how far apart they drift. If you measure a property of one particle, like its spin, you instantly know the corresponding property of its partner, even if that partner is light years away. Now, this doesn't imply we're transmitting messages faster than light in the conventional sense, but it demonstrates a mind-blowing interconnectedness that defies our everyday notions of space and separation. We're still deciphering all the implications of entanglement, but it hints at a reality that's profoundly interconnected, where parts of the universe can be linked in ways we're only just beginning to comprehend. And it's not just entanglement. Our entire understanding of quantum mechanics, including the observer effect and superposition, forms the bedrock for a vast amount of modern technology. Lasers, transistors, the tiny components powering all our computers and smartphones, MRI machines in hospitals, even GPS, they all rely on quantum principles. And the next wave? Quantum computers and quantum cryptography promise even more astounding breakthroughs. Quantum computers, by harnessing superposition and entanglement, could solve problems currently intractable for even the most powerful supercomputers. Imagine the potential impact on medicine, material science, or AI. The ripples from quantum mechanics extend far beyond the laboratory, splashing directly into philosophy's deepest waters. If observing something actually helps determine what's real, what does that imply about existence itself? Does the universe, in a sense, require an observer for it to be? Now, most physicists will assert that a measurement by a device is sufficient. But let's be honest, the boundary between a complex machine and a conscious observer can become somewhat indistinct, especially since we are the conscious beings designing the experiments and attempting to interpret the results. This notion that consciousness might not merely be a passive bystander, but an active participant in shaping reality, is an ancient philosophical concept that resurfaces in a truly intriguing, though hotly debated manner with quantum physics. Think about it. If particles only acquire definite properties when measured, and if measurement entails interaction, then our interaction with the universe isn't just us passively absorbing information. It's more akin to an active dance, where we're co-creating the reality we experience. This doesn't mean you can simply wish for $1 million and it will materialize. Sorry. But it does hint at a much deeper, more intimate connection between mind and matter, between us and what we observe, than classical physics ever envisioned. Perhaps reality isn't some fixed stage where we're merely reciting lines. Maybe it's a constantly unfolding narrative, and we're all in the writer's room. The very act of looking, of measuring, of interacting, it's as if we're helping to weave the very fabric of what is. So we've journeyed from our seemingly solid, everyday world into the mind-bending, probability-driven universe of quantum mechanics. We've seen how merely observing something can completely alter the behavior of the fundamental building blocks of our universe, whether reality truly isn't real until we observe it, as some interpretations suggest, or if it splinters into a gazillion parallel worlds with every quantum choice. One thing is certain: our conventional, intuitive idea of an independent, objective reality is at best only part of the story. Quantum physics reveals a universe that's more fluid, more interconnected, and far more mysterious than we ever imagined. The quantum truth appears to be that our relationship with the cosmos is far more entangled and participatory than we previously believed. So the next time you look around, at the world, at the stars, or even at your own reflection, just remember, you might not just be seeing reality. You might, in some profoundly deep way, be helping to make it. So what do you think? Is reality something we help create just by looking? Does that idea of a participatory universe resonate with you? Or do you lean more towards something like many worlds? We'd love to hear your thoughts, your own what-if moments, and your favorite mind-bending quantum ideas down in the comments. If this trip into the quantum truth got your brain buzzing, be sure to give this video a like, subscribe for more adventures into the mysteries of science and existence, and hit that notification bell so you don't miss our next exploration. What part of quantum mechanics just completely blows your mind? Let us know below. You're watching Deep Synapse, where science meets the soul.